Charles Liu is a professor and chair of the Department of Physics and Astronomy at the City University of New York's College of Staten Island, and an associate astrophysicist with the American Museum of Natural History and Hayden Planetarium in New York. His research focuses on, you're gonna lose me here, colliding galaxies, supermassive black holes, and the star formation history of the universe. He hosts the podcast do you pronounce it the Luniverse? And it's Dr. Charles Liu, and has authored 9 books about the physical and astronomical sciences. He earned his degrees at Harvard and the University of Arizona, and held postdoctoral appointments at Columbia University and Kitt Peak National University. He currently serves as president of the Astronomical Society of New York, and in 2020 he was named a Legacy Fellow of the American Astronomical Society. And Charles and his wife, Dr. Amy Rabb Liu, have 3 cosmically curious children, and we are so proud to claim you as one of ours. Thank you, Charles, for coming tonight and sharing your new book with us.
Thank you, Margot, for that kind introduction, and I want to thank you all for being here today. Let me tell you a minor story about my own life in Montclair. We moved here in 1997, and our daughter had just turned 3 years old. We were in our rental waiting for the right house to come along, and we just decided to walk on a Saturday into Watchung Plaza, and there was a bookstore. And I said, great, let's go. And Hannah's like, yeah, let's go. We went upstairs, Watchung Bookseller, and there was a book signing going on. And there was a person there named Valerie Wilson Wesley. And Valerie was just signing her new book, No Hiding Place. And we popped in and we said hello, and she said hi, and I said, oh yes, we just moved here to Montclair. This is really neat for us. She said, oh wait. And so she turned to her publisher and said, take this from my personal number, took it out, signed it to Hannah. Welcome to Montclair, Valerie Wilson Wesley. And we still have that book on our living room shelf all these years later. So Watchung Booksellers has been such a wonderful thing for our community for all this time, starting with our very first weekend here in this town. So my being able to be here to talk with you all about my book is just a wonderful thing for me. I feel so honored to be able to do this. So let me thank Margot and everyone at Watchung Booksellers for making this making this tremendous institution for our community survive and thrive for all these years. Thank you so much for that.
Thank you.
So let me just say this right at the very beginning so you all know what to expect. I know we have about an hour together. It is my intention to speak for only about 15 to 20 minutes in prepared remarks. I have plenty of other remarks that I could talk about, but I want to stop there because I'd like all of you who have questions about the universe to be able to ask them. So right now, if you have questions that you're thinking about, or when I'm talking, you have questions about the universe, questions about space and stars and the sky, write them down on something. Okay, get a piece of paper, remember it, and so that we can have some time for questions and answers. And let me say right now, if you are under the age of 12, your answers will be answered first. We will answer your questions first. And then people between ages of 12 and 19, we will answer their questions next. And then we will have other questions as well. And so please, everybody, be sure to have questions and be ready. Type them in on your phones, write them down on a piece of paper, or just remember them, okay? And my goal is to go for about 20 minutes. And because I have a hard time stopping talking, I want you to set your timers for 20 minutes on your phones. Set an alarm for 20 minutes on your phone, and when I hear the chorus of beeps going, I'll know that that's time to wrap up my last few sentences about my prepared remarks, okay? And then if there are no questions, then I'll talk more about a cool topic, like maybe some of my research that I do with galaxies that are crashing into one another, triggering supermassive black hole feeding, and quasar activity, which winds up shining more energy out in 1 second than our sun does in 1,000,000 years. That's fun stuff too. We'll talk about that later at the proper opportunity. Oh, here's some papers. Tell you what. Thank you, Kat. Let's just do the following, everybody. We'll take these pens. We'll kind of put them in the general vicinity and just pass some questions around. we'll take a few pieces of paper. I'll leave them kind of down
Oh,
down here. Here's a few pieces of paper for you all if you have questions. And here's some pen over there. Just pass stuff down. And you can, just ask for pens and all that sort of thing. Okay, just if you have questions, we'll try to collect them later because we all have some questions. All right, so all your phones are all set. We got our 20-minute timers going. If you haven't, okay, we'll synchronize. We'll just start at, I'll say go, and then we'll do 20 minutes, okay? 3, 2, 1, go. Okay, 20 minutes from now is sort of when we'll stop talking. The timing aspect, it's kind of funny and entertaining and humorous, but this is the whole point of the book, right? The publishers said, let's call it The Cosmos Explained. And I said, that's cool, but why don't we call it You Are Here? We are talking about the history of time. And they say, well, yeah, You Are Here is cool. That's right, because we are here, and it is today. But the proper way to think about it is that we want people to know that if you want to know about the history of the universe, come to this book, because we've explained the cosmos to you. And so that's kind of where we tried to go with this book. I am very, very happy with this book because I got the chance to tell the greatest story I can think of, and that is the history of everything. Everything, right? Now this is hard because I have a very short attention span. Okay? I'm pretty sure that if I were younger today and I were in public schools, I'd probably be on some kind of medication. But for some reason I was not done, that did not happen to me when I was younger. And I'm kind of grateful for it, although I apologize to all the people who have had to put up with me all these years doing this kind of thing. So when I had the opportunity to write this book, I had written a couple of books for this press, Ivy Press in the UK, and they said, hey, why don't you do the whole history of the universe? I'm like, yeah, let's do it. But then I'm like, wait a second. Here is a person with a very short attention span trying to write about the entire history of the cosmos. How is this going to work? And so the way that we did it was to divide it up. Every single page, every single spread has its own story. And so through taking all these little stories together, we piece together the entire history of the universe. And that's probably a good thing too, because the way the universe's evolution and the history has come up, it doesn't go 1 second at a time, every second being the same interest as every other second. In fact, much like in our lives when we have certain markings, the time we were born, our bar mitzvahs, our first child, wedding, whatever, we mark them by individual events. The universe is kind of like that. In fits and starts. It starts at the very beginning, and in the first second, a huge amount of stuff happens. And then nothing for a while, long time. And then, something happens in about 3 minutes. And then kind of nothing for a long time. Then, something happens in about 300,000 years. And then nothing for a really long time. So you see, you've got these segments of history moving around this way. So why not tell it that way? Get to the good parts, right? Watch the last episode before you watch the first 5. Eat dessert first. That's how I think about life. It's kind of what makes me happy. And so I want to write that book that way for you all. We start with the big mystery of how the universe began. We still don't really know exactly what happened. We have some pretty good ideas about what happened after the universe began. And that's by looking at the history of the universe and going backwards in time, following the laws of physics and biology and chemistry and mathematics, which we're knowing pretty well, but not great. But right at that very beginning, we still don't know exactly what happened. And so that was the first thing that I realized that I had a problem with writing this book. Because as a scientist, how do I tell people the first thing about the universe is that we don't know how it started? Right? This is a big mystery. And very often we scientists, sadly, feel like we need to be authoritative. We need to be the one where people can go to and we have the answers. This is also true, by the way, for professors, so I'm in double trouble that way. Right? So what I realized is that I have to have humility, and I have to have an understanding and realization that knowing science does not mean knowing all the answers. It means knowing how to ask the right questions. To say, you know what, we don't know. We don't know how the universe began. But based on what we do know, we're pretty sure that starting around 10 to the minus 43 second after it started, which is 0.00000000000000001 second after that Big Bang happened, the laws of physics as we know it started to work the way they do. It is by realizing what we don't know that we make the progress in our lives, in society. And just to fast forward real quick to a part where we're talking about the history of human science and understanding. It was in 1900 that a huge amount of science had been figured out. Thermodynamics had finally been understood. Electromagnetism, we were starting to figure out how to build circuits. Electric generators, we were able to build heat engines, steam engines. The Industrial Revolution was well underway. It seemed like there were no more mysteries to solve. In 1900, famous physicists were asked, what kinds of things do we still have to think about? And there was a very famous scientist, his name was Lord Kelvin, William Thomson, Lord Kelvin, one of the founding pioneers of telecommunications. He was essential in creating some of the supplies and equipment based on pure physics and then later on applied physics. He was an entrepreneur that helped lay the first underwater submarine cables from the UK to the US and Canada. So he was a wealthy man. He was given a lordship, so he was known as William Thomson Lord Kelvin. And he was also a brilliant scientist. And Lord Kelvin was asked to give a talk about what mysteries were still going on in the history of the world. What science questions still needed to be answered. And he said, yeah, you know what? We're pretty good at physics right now, but there are two little clouds that block the clear sky. Two little clouds that block the clear sky. That, for better or worse, over the past 100-some years has been taken by many people to say, well, even a great scientist like Lord Kelvin said, we know physics, we only have two little mysteries we don't know about, right? I went back and read his talk, read the paper that he did in 1900, his talk, and I found a completely different story. I found a story that he said, what we know, what we see, is pretty clear. But these two clouds here may be hiding huge amounts of unknown things. And what are those unknown things? And he started talking about those things. And those two things turned out eventually to become general relativity and quantum mechanics. The two great modern scientific contemporary theories of our universe. He foresaw, even though he was perhaps the best known physicist of his time, that there was much left to be understood. And he could only see them as two small clouds that were blocking the sun just a little bit. He understood that what he didn't know far exceeded what he did know, even though what he did know thought or seemed like a lot. And it was from there that we go further and further into the mysteries of the universe today, as we look back toward the Big Bang and the history going forward. The book has basically 12 sections. We start with the very, very beginning, the history, that Big Bang, what the heck happened to start the universe? And then the formation of particles in the universe. Those things that you might have heard of, quarks, fermions, bosons, and then things like electrons, protons, neutrons. Those things all started to happen within about a second. But then the first real elements that form, what we call nucleosynthesis, the atomic nuclei, started forming around 3 minutes after the Big Bang. By about 10 minutes though, it was all over. The universe was filled with particles, some of them with a lot of mass, some of them with no mass. But of the things that we're familiar with today, 3/4 of the mass in the universe was hydrogen. And then 1/4 was helium. So if you were able to, blow up a balloon back in those days, it'd be very, very exciting. We had a lot of fun. I think like this every hours from it. That's how I would think about the early universe. And then we go on from there. There's a long period of time where not a whole lot happens, like I said. But the universe keeps getting bigger. And if you want to tie the whole history of the universe from beginning to now, it's that it keeps getting bigger. The universe is still getting bigger all the time. And thus, time on the cosmic sense can best be kept by measuring how much the universe has expanded. Those clocks, the vibrations of atoms and molecules, Earth going around the sun, those all came later. If you want to measure time passing in the history of the universe, you start with its tininess and you go on to its largeness. And then finally, 380,000 years or so after those first 3 minutes, the universe got large enough that matter and energy could start doing their own thing. Energy streamed across the universe, and later on to be generated or to be destroyed in terms of those little particles, which we call photons. Not those big things called photon torpedoes. Those are different things. Okay. Oh, by the way, it's May the 4th be with you. Star Wars, Star Trek. What do you think? All right. Just saying. But anyhow, the point of that thing, the universe expanding, the energy wound up filling our universe. As the universe got bigger and bigger, that energy got sparser and sparser, but it's still there. It's called the cosmic microwave background today. And the matter, what did the matter do? It started to feel the influence of gravity, unfettered by all that light that was kind of dashing in and out between them. By the decoupling, the separation of the effects of matter and energy on one another, things could start to aggregate, and we started producing things like stars, galaxies, and black holes. Black holes are fun. Just by themselves, they have their own little, section in the book because, of course, we love black holes. Just want to let you guys all know, black holes don't suck. Okay? Black holes don't suck. You cannot be hoovered in if you're going by a black hole like, the black hole's pulling me in. No, that's not how it works. You have to fall into a black hole. So if I were a safe distance away, if the sun suddenly became a black hole tomorrow, purely gravitationally speaking, we would not be sucked in by it at all. We would continue in our orbit along our merry way. But if you do fall into the black hole, you're not coming out. Right? That is your new home. And in fact, there is a song that tells that story. Yes?
When did the Big Bang start?
When did the Big Bang start? That's great. I will answer that immediately. And then we'll continue with this, and we'll answer more questions in what? 10 minutes? 7 minutes? Okay. The universe, the Big Bang started 13,800,000,000 years ago. I know. Oh my. How old are you, may I ask? 6. Almost 7. Congratulations.
My birthday is May 27th.
Oh, May 27th is a wonderful birthday date. Great job. Congratulations, soon to be 7-year-old. You only have 13,799,993 years less than the universe has been around. That's great. So, let me skip forward because the book has a lot of stuff in the middle. But this wonderful question asker kind of brings me to a point that I want to get to in my prepared remarks. And that is the issue of time and how much time we have. And we all have different amounts, right? And I've been asked that a lot too. Say, well, you know how old the universe is. You know that the sun is 4.6 billion years old. You know that the earth is almost 4.6 billion years old. You're only around 100 years, give or take. Does that depress you? It's like, you are so insignificant, right? Not to mention the age of the universe, and then there's the size. I mean, compared to the earth, compared to the stars, how small are we, right? And so, on the one hand, it is very humbling. But I tell it another way. I think of it a different way. And I thought about this all throughout as I was writing this book. The last several chapters of this book, the stories of them, are about life, are about humanity, are about society. Do we actually matter in this grand scheme of the universe? How important are we or unimportant are we? And what I wanted to say in the book was we are just as important and just as ordinary as every star in the sky. as every galaxy in the universe, and as every mayfly on a pond. If you think about the whole history of the universe and all the things that happen, there is a natural tendency for us to feel either very special, like, you know, we are the chosen ones or whatever, right? Because whatever magical, amazing thing, the whole universe was built just so we could be here, right? There's a real strong feeling of that, as so many people have. And at the same time, there's this sort of existential dread, right? Yeah, I was born. I'm out of here at some point. No one cares. It'll be all fine. What am I even doing here, you know? Why don't I just eat dessert first? Well, my answer is yes, eat dessert first. But remember how cool you are and how normal you are. In other words, we are as ordinary and as amazing as everything else in the cosmos. That gives me a sense of liberation. As I was writing this book, I really felt like, yeah, I'm just telling the story of great stuff and we can feel good about everything. Right? We don't have to feel bad about it. We should acknowledge our happinesses and sadnesses, our successes and our failures, but in the overall arching scheme of history, we're pretty cool. We really are formed from just the leftover stuff that formed our sun, that formed our planet, that's just kind of sitting around near the surface of the Earth a little bit, that happens to get a little bit of sunlight on the top and a little bit of radioactive decay heat coming from the interior and stuff like that. But we're here. And if you think about us as a system, right, we human beings have more living creatures living on us and in us than there are human beings on Earth. We are an ecosystem. We are a world. And the people, or the creatures that live on us and in us have no idea. What do we have no idea about? I'm not hypothesizing or supporting, shall we say, the so-called Gaia hypothesis, which suggests that Earth is a sentient creature, or even the Medea hypothesis, that Earth does its best to make us extinct. Right? What I do know is that the laws of nature, as we understand them up to this point, based on the stuff that I was talking about in here, really led me to believe that we can be really happy with what we got. No matter how great or how not great it may seem, it is as much a part of the universe and the story of the universe as those stars over there that you're going to see rise in a few hours, or the galaxy in which we live, or the Andromeda galaxy just going to come in and smash into us 5 billion years from now, probably wiping out our galaxy if the sun doesn't go red giant and incinerate the Earth first. That's okay. No big deal. Don't change your retirement plans. We are fine. If you want to think about the cosmos explained, maybe that's sort of the takeaway that I'll take you for now. And that is that years from now, pretty much everything is going to be different. It used to be the same, but then it became different. And then it became the same again, and it became different. And that's what's going to happen for us. Right now, we're in one of those calm times. Nothing really changes much in the history of our universe for another 100 billion or a trillion or so years. But it looks like, based on what we understand, what we don't know, there are going to be some changes that happen in our universe many, many billions of years from now. So, right now, if we were to say, what are the two clouds on the horizon? In the same way that Kelvin foresaw the general theory of relativity and quantum mechanics, what might we possibly foresee today? For an astronomer, that's easy. There are two things that take up 95% of the budget of stuff in the universe, which we have no clue about. Zero, zip, nada. One is so ambiguous we don't know what it's called, so we just call it dark matter. It's nothing that's made up of protons, neutrons, and electrons. But for every pound of us, protons and neutrons and electrons there are 5 or 6 pounds of that stuff. It outweighs us, and it is shaping how our stars and galaxies and clusters and superclusters are aging. Thank you. Perfect. Others will be going off in a moment too. The second part is even bigger. If you count up using E equals mc squared, the amount that this stuff has compared to the dark matter I just talked about, that stuff is 3 times as much. But it's not even matter. So we call it dark energy. 95% of the stuff of the universe is completely unknown to us. So the 5% that we're part of is pretty cool. And I'm pretty happy with it. And so that's my general introduction to you all to the Cosmos Explained. And I would like now to answer any questions you all have, starting with these wonderful people who are under age 12. Okay? All right. Can you wait on just a second? Because you asked a question first. I'll ask you these questions, and I'll come back to yours. Is that okay? And if there's anybody else back there under age 12 want to ask a question, you will go next. All right, why don't we start with this person? Hello.
How did the Big Bang stop?
Why did the Big Bang stop?
No, how?
How did the Big Bang stop? That's a very good.
How did it start?
How did it start? That is a great question. We still do not know the answer to that question, but there are 2 scientific hypotheses from which there seem to be pretty good evidence that we can work on. We still don't have the technology to prove them. Here are the 2 best guesses that we have. Okay? Guess number 1 is that deep inside of all of space and time, everything is wiggling and jiggling, but we can't see it because our eyes can't see that detail. Okay? Wiggling and jiggling. You know, wiggle and jiggle with me? Wiggle, jiggle, wiggle, jiggle. Yeah, that kind. I used to do that all the time when I was in school. My teachers were like, "Oh, come on." Right? I used to drum on the desk. I remember very clearly once in 5th grade, I was like, and Mrs. Wigston from Northeast Elementary School, not this one, but a different Northeast Elementary School, said, "Charles, stop it." And I stopped it. And I thought for a second, I was like, how did she know that that was me? From all the way across the room, how did she know that I was the one that was tapping on my desk? Obviously she knew, because I was the only one who would do that, ever. But anyway, question, possibility, all that jiggling that we can't see, they're called quantum fluctuations. Pretty cool, right? And if one of those quantum fluctuations from way, way long ago, for some reason, instead of just jiggling, like got out of control and went woo, actually made that sound too, woo, then that Big Bang could have started that way. Is that cool? That's one hypothesis called quantum fluctuations. The other hypothesis is even more pretty amazing, and that is the idea that our universe was actually produced when 2 other things, kind of like the universe, but not exactly like our universe, connected. Have you ever taken like a soap bubble over here and a soap bubble over here, and they kind of, push them together in the bathtub or something like that? I do that all the time still. Push, 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 and then whoop, they all come together. It's like, yes, I made them come together without popping. For a moment there, right, before they become one bubble, there's a little 2-bubble thing, and then there's a little skin between the 2 of them. That other hypothesis suggests that we are the skin of the bubble. Isn't that cool? Those other bubbles are 5-dimensional structures, loosely known as membranes. And when those 2 5-dimensional structures come together, they create a 4-dimensional skin. And guess what? Our universe is 4 dimensions: length, width, height, and time. But because we can't understand how those things connect to one another in terms of our modern time, those soap bubbles are still connected. Maybe they'll pop open again sometime. Maybe they'll stay together for a long time. Maybe they'll come to a whole new bubble. We don't know. But those are 2 possibilities how the Big Bang got started. Great question. Thank you very much. Yes, your question.
So when debris falls into a black hole,
Yeah.
what happens to it?
When
Does it just go boom and disappear, or does it
wonderful question.
what happens inside of a black hole?
This is great. Let me tell you.
Inside of people's
Well, I was, a few years ago, I was interviewed for a story which was out in the world for a brief period of time, which was titled the three things that every astrophysicist gets asked sooner or later. If I'm at a cocktail party and people find out I'm an astronomer, sooner or later I get asked one of three questions. I've already been asked two of them right now. Okay? One of them is, how did the universe start? The second one is, what happens when you fall into a black hole? This is a fun thing to answer. When you fall into a black hole, it's kind of like trying to squeeze all the water in a bathtub down the drain all at once. You can't fit it all. And so it swirls. And it creates a vortex. Or, as Isaac used to say, vortex, vortex, vortex. It was awesome. At the end of every bath, it was like, I want to see the vortex. Yeah. He couldn't even say, I want to see them. He was like, almost two. Thanks, Isaac, for letting me tell that story. So, it turns out that about 90% of the matter that falls down toward the black hole never gets there. Because as the stuff falls down, it starts moving faster and faster in the vortex, swirling and swirling and swirling. Soon, it approaches the speed of light. And when matter, even the smallest particle, moves as fast as the speed of light, it gets converted into a tremendous amount of energy. Even the amount of matter in a paper clip, if it were converted into energy, would have more power than 20,000 tons of dynamite. So it's really, really powerful. So all of that energy starts shining out. And so 90% of the matter falling in never reaches the black hole. It gets sprayed away by all this tremendous energy that flies out. So that's too bad, right? Darn. But that is amazing, that 10% of the matter does wind up going inside the black hole. Okay? That 90% is super bright and shines and really beautiful. But those 10% that goes in, remember, they're going closer and closer to the speed of light, right? When they reach the surface of the black hole, called the event horizon, they are going at the speed of light. And when something goes at the speed of light, a few things happen that are really unusual. Number one, they turn into energy. Number two, you can't see them anymore because their light has been stretched by something called gravitational redshift. And third, as they fall, you watch them go slower and slower through time. It's a process based on one of Einstein's theories called the special theory of relativity. So, for example, let's say you and I were riding a spaceship together, heading down in toward a black hole. For some reason, we're not, being destroyed yet, right? We're still matter. We're turning into energy, but we don't really know it yet. We're kind of going down. We're singing like some happy song that has to do with astronomy. I don't know. Let me think. If you want to run away with me, I know a galaxy and I can take you for a ride. How's that? Anyone here over the age of 25 know that song? Dua Lipa, that's right. Yes. If you want to run away with me, I know a galaxy and I can take you for a ride. Okay, so we're just like humming and having a great time. The Spotify's going, we're having a great time. But if my friend were out and your friend were out in a further out spaceship, like listening to our broadcasts, like seeing what's happening to us, what they would hear as we get closer and closer to the black hole would be, if you want to run away with me, I know a galaxy and I can take you. Kind of like that. Because the time is moving more and more slowly as we observe you. Eventually, time stops for us, we fade away, and the black hole's event horizon rises to meet us. And we become part of the black hole as it grows to include us. Now, if the black hole is just the wrong size, we would be squished and turned into a stream of atoms and be like, ah! Right? But under the right circumstances, we would just be singing Dua Lipa and having a grand old time. But once that gets in, I'm sorry, I do not know what's going on inside. There are some people who think that there might be some interesting ideas of how behavior might happen inside a black hole, but no one has any proof yet. In the book, I do talk about some of those hypotheses. There's something called the holographic principle. There's some other things about singularities and things like that. Enjoy that stuff.
Right.
But we don't know the actual answer yet.
Right. So for all we know, you could be trapped in an infinite state of frozen.
Absolutely. For all we know, we could be trapped in an infinite state of frozenness.
So time has stopped completely. And
Time is
it's
stopped completely. Yes, and we'd be like, try to send out one last little signal to Anna before we froze solid. Let it go, let it go. But actually, we wouldn't be able to send out that signal because the event horizon of the black hole is kind of a pretty tight boundary. Yeah, pretty cool, right?
Yeah.
I love it. Thank you for your question. All right, I think are these under like 12 to 18?
No, these are 18 plus.
18 plus. Uh-oh, okay, we got to go 12 to 18. Who's got 12 to 18 questions? Okay, all right. You are all welcome to ask more later. Oh my gosh. Is it appropriate to consider Earth as an organism? Great question. This leads to a part where I only talk about briefly, but I do mention it. What is life? If we ask 100 biologists what is life, we get 110 answers. Right? And astronomers have the unique privilege of not only thinking about what life is, but how it got started. Because we're pretty sure that there was not life on Earth before there was Earth. So where did it all come from? And so we're asking ourselves what life is, and today we kind of have a sense of what life is, right? Life, we all kind of have to start from something that we weren't before. We all kind of grow or change slowly, and then we reproduce somehow. Some parts of us wind up going off and creating other living things similar to us, and then our life cycles end, and our materials get recycled to become other things, right? That seems to be like a life cycle. A friend of mine, Maggie Turnbull, in graduate school, after she got her astronomy master's degree, decided to get a master's degree in microbiology. Because she said, you know what? I challenge you to tell me, what is it about any definition of life where a star is not also alive? Where a planet is not also alive? Where a galaxy is not also alive? So if you take into account the most general definition of what life is, being born, growing, reproducing, ending of a life cycle, yeah, Earth is definitely alive. But then we have to think a little bit more detailed carefully, right? If something is alive, does it mean anything really, really significant and important? Right? Yes. But does it mean anything more important than what we already know and experience? This is a philosophical question that is beyond my pay grade. And therefore, I do not try to answer that question, but I do pose it. In all humility, I tell everybody, yeah, imagine Earth is alive. You know, as I said earlier, we are alive. But if there were the cool bugs that live inside our intestines and help us digest our food, if they considered themselves alive, would they consider us alive? Would they consider us so huge and so amazing, such a system that there is this thing called intelligence or sentience that runs us, right? Somehow we put a really big emphasis, we humans, on life that is a lot like us. That it is more important to be, say, for example, nice to people like us than to creatures that are not like us, or environments and so forth. And that might be true, because we should survive, right? It would be nice if we lived and were able to survive. But at the same time, the whole concept of what is alive and what is life and what is not alive, and all that starts to break down when we're looking at it at this point, at this level of sophistication that we are trying to do. So, if anything, it makes me feel ever more grateful for my own life, and that if I'm able to influence, even for a short period of time, other life in positive ways, is worth it, is okay. If I don't succeed, let's say I want to change the world tomorrow, and I only change it like a tiny, teeny, weeny bit tomorrow, that's okay. I didn't fail yet. I'm still working on it, and that's all right. So I hope this, in a broader sense, answers that question. Is Earth truly alive, if we consider it? We can even think about it, from a truly biological perspective. What if there was some other DNA-based life that showed up on Earth, carried by a comet or something like that? Does that mean that there's actually a living, reproductive system? That is only one of many ways that the Earth could have reproduced or been reproduced by something else, depending on how you think about it. So, yeah, it's pretty cosmic, right? Woo! I have fun with it. Okay, got another question. You gotta start jotting down questions, and we gotta start raising hands, too. All right. What do we think black holes lead to on the other side? Ooh. What do we think black holes lead to on the other side? For a long time, people figured that black holes were rips in space and time, or possibly channels to some other part of the universe. Okay, in other words, black holes here led to white holes there, and stuff would come out on the other side. We didn't have really any way to prove otherwise. But over the very many decades that we've observed stuff, we have not seen white holes in our galaxy or in our universe. We see things that are very bright, but nothing that can only be explained or can best be explained by stuff coming out of a former black hole from somewhere else in the universe. So we're pretty sure that black holes are not channels or conduits within our universe to another spot in the universe. Although that might be possible mathematically, we don't see any physical evidence for that yet. Instead, what has happened is, in the past, I would say 10 to 20 years, folks like Stephen Hawking, up to the time of his passing a few years ago, and other theoretical scientists, Kip Thorne, for example, who recently won the Nobel Prize in Physics for his work on black holes, gravitational waves specifically, but really, he did black holes too. People like that, they've come to the conclusion that more likely than not, instead of it being a tunnel from one part of something to another part of something else, it's more like a water balloon. You have this thing that kind of fills, and if you imagine a water balloon that's stretched tight, the water fills up more and more on the bottom, kind of dangles, drip more and more and more. There are other biological analogies I can use, but I'd rather use water balloons. And it just gets stuck there, and it can't come back out, right? So really what they are repositories, some sort of extra concentrated, inaccessible matter or energy or something, or space-time. That's not really part of our universe, but not really part of any other universe either. And it looks like that black holes, if you give them enough time, eventually start losing their mass. Through various quantum mechanical properties such as quantum tunneling, but really more through sort of fundamental thermodynamic arguments, there's this thing that we named after Stephen Hawking, something called Hawking radiation, that will cause objects like black holes, even black holes, shall I say, to lose their energy over a long, long period of time. So how long is that, right? We are talking for a black hole that's, say, the one in our Milky Way galaxy, what we call Sagittarius A star. Take a 1 and put 85 to 90, maybe even 100 zeros after it. And that's the number of years it would take for that black hole to have all of its mass be reabsorbed into our space-time. That's a really long time. Remember, our entire existence right now is only about 1 with 10 zeros after it. You got to stick another 80 or 90 zeros after that to even get to the black holes disappearing. But when that happens, basically it's like the water balloon, like the water is slowly evaporating out of that little tiny bit of water, a little tiny aperture, and slowly but surely space-time returns to normal. There are some even more exotic ideas about how black holes work, but suffice it to say that at the moment, We don't think that they're pathways to somewhere else. But they are conduits into someplace else. And maybe that someplace else in there, if it follows different rules of physics, different laws of space and time, maybe it is as much a universe unto itself as the very universe that we live in today. A question from here and a question from there.
Yeah, I'm sure this question falls into your cocktail party.
Uh-oh, cocktail party.
But two questions, which are kind of probably both cocktail questions. But what if the universe is expanding? What's there before it's expanding, and what was going on before the Big Bang?
Mm-hmm. Great question. The universe is expanding. What is it expanding into? Or what was there before the expansion? What you're asking is indeed very fundamental. And the idea of what is beyond what we can see, right? What exists beyond existence? I think I heard somebody else say, right? That is completely the right question to ask, because we don't have an answer yet. I have to defer to my mathematician colleagues and friends and wife and child to get some insight into this. You see, you and I, not being abstractly versed in mathematical multi-dimensions, are used to thinking of space as length, width, and height. So if we got something that has length, width, and height, obviously it has to fit into something that also has length, width, and height. But my mathematically very advanced relatives and friends explain to me often, because I don't get it the first time, that that's not necessarily the right way to think about it. We can exist in an environment that does not actually have to conform to what we think of as length, width, and height, and even time. So that what we originate from, kind of the question that was asked by this nice young person here earlier, right? Where did the Big Bang start? How did the Big Bang start? It may well have started in a circumstance before this thing we call the universe, length, width, height, and time. Any of those dimensions existed. So if I say what is before the Big Bang, you're assuming that time existed. But based on our physics now, time only began to exist at the Big Bang. Similarly, if we're trying to say what did the universe expand into, we're assuming that length, width, and height existed before the universe began to exist. But it didn't. So we have to think about dimensions and dimensionality and spaces not like the way we think of our space and time here, but in abstract possibilities of things that can be connected in ways that we don't really experience on a daily life. So I don't have a really good answer to your question, except that I will say that there probably existed things other than what we know as space and time. And then when we began to exist as space and time, we could not access those things. But maybe we will someday, if we are able to think deeply about them.